organizing such an already stimulating, and I can't wait for the rest of it, kind of meeting. I'd like to begin by saying that one of the last meetings I came to at Chapman was sufficiently stimulating that some of the data I'll be showing today comes directly out of an idea that I got at that meeting, and I'm looking forward to being back in 3 or 4 years with data from whatever ideas I steal from you all at this meeting. So I want to tell you about a few things. I want to talk about 2 novel applications of entanglement. One of them is compressing 3 qubits into 2, which has very little to do with the other themes of this workshop, but I hope you'll find it interesting. And the other one is making 1 photon act like 100, which many of you will recognize is directly related to weak value amplification. And some of you may recognize getting 100 heads on 1 coin and understand what I'm referring to over there. But the way I like to think about this talk is the shallow dip before the deep dive. I didn't know that today was supposed to be a deep dive, and fortunately I'm speaking early enough with enough big sharks coming after me that I thought I would just play it gentle, introduce some of the questions, and not try to answer any of the deep ones yet. I look forward to us all arguing in the course of the rest of the day. So before I do that, I have to give 2 rather late announcements. One of them is that at Toronto, we're advertising for an assistant professor of experimental quantum optics. And the deadline used to be a few days ago, and now it's a few days in the future, and I finally thought I would just block that out. Open until filled, but if you know anyone who might be applying or interested in applying for positions in experimental quantum optics, have them hurry up and send an application right away, because we'd like to find the best person possible, and if there's any chance we didn't reach the right candidate yet, help us out. And another very time-sensitive warning. Hopefully many of you already know about this. But at Toronto, at the Center for Quantum Information and Quantum Control, we award the John Stewart Bell Prize for research on fundamental issues in quantum mechanics and their applications every 2 years. The next one will be awarded next summer at our biennial conference in Toronto. And nominations are due by December 15th, 2014. So you still have a while. If you can think of work done in the past 6 years, which merits this kind of an honor, we'd love to hear about it. So if you've gotten that email address, that's great. Otherwise, ask me later, and we'd love to see nominations. All right, so here are the 2 things I want to tell you about. The first is when the measurement of photon number of a single photon can yield a value of 100, a question that should sound familiar already. The parts of that talk are going to involve a little introduction to what we call giant optical nonlinearities, measurement of the phase shift of a single post-selected photon. That's work we just completed, and they're submitting right now. And finally, weak value amplification of the phase shift, not really of a single photon, I should have said due to a single photon. And that's work that we're just about to start writing up. It's the stuff that was inspired by the previous meeting here. And I believe that this is the first example of a weak measurement done by deterministic entanglement of 2 distinct systems. Almost all the weak measurement experiments we do involve using 2 different degrees of freedom of the same system. And one consequence is that they can be thought of in also very simple classical terms. Many of the electromagnetic systems can be described perfectly well using classical electromagnetism, or the quantum theory if you prefer. Once you're dealing with 2 discrete systems that truly become entangled, that's no longer possible. You have no option but to use the full quantum treatment. And as far as I know in the past, the only example where the weak measurement has involved distinct system and pointer has used non-deterministic quantum logic gates. So this is the first deterministic version. And then this cat is alive. The cat is compressed but perfectly healthy. And that's exactly what I'm going to want to demonstrate in part 2, that we've learned how to take Schrodinger's cat and make it occupy less space, but in such a way that we can extract the full healthy cat at the end. So that's exactly where we're going. And along the way, I'll introduce the questions about signal-to-noise ratio that come up in weak value amplification, so that John and Andrew and everyone else can spend the rest of the day contradicting me, I suppose, but we'll see where that leads. So first of all, these are the people who did the work. We do laser cooling experiments and down conversion experiments. The group has an atoms component and a photons component. And the people in red are the ones who contributed mostly to the work I'll be telling you about today. Dylan Mahler and Lee Rosema were leading the photons effort. And Amir Feyzpour, Greg Mahovsky, and Mateen Halaji led the work that I'll really be telling you about right now on the interaction between light and matter. A lot of important assistance from Alex Hyatt, Janelle Johnston, and inspiration from many longer-term collaborators such as Morgan Mitchell. Theoretical support on this work was largely due to Pete Turner, Robin Bloom-Cahoot, and always some interesting discussions with Howard Wiseman, Janos Vergu, and John Seig. All right, so when does one photon act like 100? Let me go back to my more narrow-minded quantum optics motivation, which is single photon level optical nonlinearity. Optical nonlinearity, for those of you who aren't optics folk, is just a fancy way of saying the interaction between light and light. Right? Normally, light doesn't interact with itself. That's why I can shine this beam over here, and if you open the windows again and the sunlight comes in, those photons from the sun are not going to knock my red laser photons out of the way and stop them from getting where they're going. Light beams just travel easily through one another. When there is nonlinearity, however, that's not quite true, and there are interactions between photons and other photons. Those interactions are typically so weak that if you just wanted to put a dimensionless number on them, you would put a number on the order of a part in 10 billion. So typically when we do nonlinear optics experiments, we take trillions of photons, and we begin to see these interaction effects, which means that most of the time people who study individual photons don't get to use those effects, and people who study nonlinear optics don't have to think about individual photons, don't even have to think about quantum mechanics. Obviously, the field becomes more interesting when you can have these two things at once. Start to ask, what if two photons interacted so strongly that they could form a bound state, where they could repel each other and never be found in the same place? This has been one of the holy grails of nonlinear optics for quite some time. And my old advisor, Ray Chow, along with Ivan Deutsch and John Garrison, was talking 20, 25 years ago about ways of making two-photon bound states. At the time, I think they proposed that you could do this in an optical fiber as long as the optical fiber extended to Pluto and had no absorption whatsoever. Since then, there's been a lot of progress. I think now you only have to go to Mercury. No, that's not quite right. You can actually do much better, and similar results have been observed in photonic crystal nonlinear fibers, for instance. But interestingly for me, there have been proposals, in particular by Kainomoto and Bill Munro, that suggested that if you could make these nonlinearities much bigger, using effects like electromagnetically induced transparency, a well-known atomic coherence effect, but still not on the order of unity, maybe on the order of a part in 1,000 or a part in 1,000,000, you could actually leverage that into a technology for things like quantum computation. And I mean deterministic, scalable quantum computation, as long as you could measure the effect. The effect doesn't have to be any particular critical size. It just needs to be big enough that you see it. So we started pushing towards that. And in parallel, I'll say these giant nonlinearities are still actually very weak. So I call them weak giant nonlinearities. In the past 2 years, people have also demonstrated giant nonlinearities using a system called Rydberg atoms. And in particular, there are some beautiful results from Lukin and Vuletich's group that demonstrate essentially phase shifts on the order of 1 for single photons. This hasn't yet been extended to the particular geometries we're talking about, but that's almost certainly the wave of the future, or at least one of the waves of the future. All we want to do, though, is have some medium. I've labeled it XPM here, which stands for cross-phase modulation, which just means that if you send a signal through here and you send another beam, a probe, through the same medium, the probe picks up a phase shift that depends on the intensity of the signal, or the number of photons. And ideally, that means that if you sent 1 photon through here, you'd be able to detect the phase shift on this probe beam. Well, how does that work? If you think about what the probe is doing, we're going to tune it close to some atomic resonance. The atom has some index of refraction, and as a function of frequency, it looks like this. It goes through a steep slope right at resonance. Now, if you add a second beam, this signal beam that we have, it turns out that the influence of the electric field in that signal beam is to polarize the atom and change its energy levels. So it shifts these two energy levels away, and suddenly this probe beam that used to be on resonance is no longer quite on resonance. It shifted a little bit. And when it gets shifted, it thinks that atom has a somewhat different index of refraction. That changed index of refraction gives you a changed phase shift. So you directly see the presence of the signal pulse just because it changed the properties of the atoms, which in turn are affecting the light. No direct interaction here between the two photons. So that's something known as an AC Stark shift. Stark shift is just the shift due to an electric field, and it changes the index of refraction, and hence the phase. That's still a very small effect. It's nice to use the resonance. It makes it more significant than if you just used some optical fiber or something like that. However, if you use this effect called electromagnetically induced transparency, that was pioneered by people like Steve Harris and Boris Stoichev back in the late 80s and early 90s, you can get a much, much larger effect. And I'll try to give you a schematic of why that's true. EIT, electromagnetically induced transparency, is the idea that you can take an absorbing medium, like an atom close to resonance, and turn it transparent by turning on an extra beam of light. So if you look at just this triangle on the left, what we call a lambda scheme, because it looks like a capital lambda, we've got 3 atomic levels, and we've got a probe beam that would normally be absorbed on this 1 to 2 resonance. But if you turn on a strong coupling beam over here at the same time, it turns out it etches a hole in that absorption. Now what it means is instead of this dashed absorption curve that peaks on resonance, suddenly you end up with perfect transparency right on resonance and absorption only off on the sides. The flip side of that is that if you change the absorption, you also change the index of refraction. And this steep feature here leads to an extra steep feature in the index of refraction there. Remember how our nonlinearity worked. You change the detuning, that changes the index of refraction because you move along the slope. Well, the steeper the slope, the bigger that change is going to be. With a normal atom, that slope is determined by the natural line width. It's just given by the lifetime of the atom. We can't play with it. This slope here is determined by the strength of the coupling beam. And you might think, well, how much power can you get in the coupling beam? If you could make it strong enough, you'll get a huge effect. But no, it's better than that. It turns out as you turn the coupling beam off, the width goes to 0. So the great technical difficulty that you have to achieve is to turn this thing down and down and down and almost off. So in principle, you could get an arbitrarily large slope here. There are obviously technical considerations, but we want to turn that as low as possible, get the biggest possible slope, and then get the highest sensitivity. The narrower that transparency window, the larger the nonlinearity we'll get. And of course, this AC Stark shift, again, I should have borrowed a light. Yeah, there we are, is intensity dependent, which means that the shorter you make the signal pulse, the bigger its peak intensity is going to be, and the bigger the cross-phase modulation is going to be. So what we really want to do is take our single photon and make it very short in time, which means a broad frequency distribution, in order to get a big effect. Well, here's a problem that some people in this room have studied and was first pointed out to us by a sabbatical visitor. What's the use of making a really, really narrow transparency window if you want a signal pulse that's very, very broad? And I thought we had the obvious answer to that. We were never planning on taking our broad 7 megahertz single photons and sending them inside the transparency window. We were going to send them off on the right-hand side here as the signal and use a very narrow probe beam inside the EIT window. Except there's still the argument that if you've got some effective medium that has a narrow line width, let's just say 100 kilohertz for the sake of argument, then that means it has a response time that's 1 over that bandwidth. You should think of this thing as having a 10 microsecond response time. And if we send in our 40 nanosecond or 100 nanosecond pulses, how big an effect should we really expect with that slow response time? That worried us for a while, but we did an experiment recently, and the theory is on the archive, and the experiment was about to be submitted until we realized that it didn't fit the theory. So we trust the theory at this point and have to retake the data, which is kind of embarrassing. Anyway, the experiment gives the important point here. The disagreements are sort of minor. What we're looking at here is, as a function of time, the phase shift observed on a probe beam. And if you look at the black curve first, what you see is if at t equals 1, don't ask me why it's labeled that way, we send in our signal pulse, we see around the width of that pulse this very short response in the phase of the probe. And then if we narrow the EIT window, we go from this the black curve to the blue curve, and you see the signal gets bigger, just as I promised. But as you keep doing this until the EIT window gets narrower than the bandwidth of our signal, that saturates. This thing stops growing. We were happy that it stopped growing because the fear was that it would start getting smaller. And it turns out if you do the scaling right, No, it doesn't get smaller. It stops growing, but that's all. And while it stops growing, the width of the pulse gets longer and longer. That's the role of the response time here. The atoms remember our 40 nanosecond pulse for the next 10 microseconds, which is great for us because remember, our only job is to measure the effect of that photon. The longer the atoms remember the photon was there, the more time I've got to look for the signal, the better my signal to noise is. So although this isn't as good an improvement as increasing the amplitude of the signal, it's still very nice. It still means if we could go to the narrowest possible EIT window, we'd get the best possible detection of that photon. All right, so here's sort of what the experiment looks like in cartoon form. We've got a cloud of laser-cooled rubidium-85 atoms, and we send a bunch of beams through them. At the moment, we've got a signal and a probe pulse counter-propagating, so we have two telescopes aimed at each other, so they're focused onto about 20 microns in the middle of that cloud. And this coupling beam for the electromagnetically induced transparency comes in from the side. And there are some problems with that, but we needed to do it for the current iteration of the experiment. And this probe pulse, actually, there are some tricks going on. It contains two different frequencies, so we can do a kind of beat note interferometry, which means that when the probe comes here to a fast detector that then goes to a spectrum analyzer, we're able to measure the phase shift on the relevant component of that probe. So we have a source that will generate single photons with locked to the rubidium line with approximately the right bandwidth. At the moment, our source is a little bit too dim. It would take us 6 months of continuous data taking to get a good signal. So we've got to improve the source and improve the signal before we can do that experiment. And for now, we decided let's just start with classical pulses. Well, there are no such things, but quasi-classical pulses, laser beams, coherent states of light, at a very, very low intensity level. So here, as a function of the average photon number per pulse, I show you the cross phase shift. And we begin up here with 10,000 photons per pulse. Above that, the effect begins to saturate. And we see this nice linear dependence as we turn the average photon number all the way down to 1. And this, as far as I know, is the first time that's been done in free space. We've seen for pulses with really just one photon on average, about an 18 microradian phase shift on our probe beam. So clear observation of the phase shift at the single photon level. Now, at the single photon level is one thing, but again, we wanted to see the effect of real single photons. And there's something nice going on here. Remember, the photons are going through this transparent region. So our signal photons go through the atoms, and we didn't destroy them while trying to measure them. We have a chance to detect them later on. So let's see what we can do. As we turn the intensity down more and more, here's the phase shift for 5 photons, about 60 microradians. 2 photons, we still see it. Just to make sure we're looking at the right thing, change the sign of the detuning. That's supposed to change the sign of the effect. That all works. But then we add an extra detector for the signal photon. And we say, well, let's look at what happened when the detector clicks and what happens when it doesn't click. It turns out every time the detector clicks, we get extra information. That click tells us, oh, there's one more photon than when I didn't go click. There's the photon that just made me go click. And you can work that out more carefully. You can do the statistics, or you can think of it a bunch of other ways. But you can really demonstrate that the inferred number of photons that must have been in this medium a moment ago is 1 higher when I see this detector click than when I don't see it click. So that's what these blue points are. We see a larger phase shift by 1 unit, 1 single photon phase shift, every time the detector fires. And we can do that at lower and lower intensities, down to 1 photon per pulse, and even down to half a photon per pulse. In other words, a pulse that roughly half the time has no photons at all, roughly half the time has a photon. And we worked out that when our detector doesn't click, we should say, oh, there was probably only 0.3 of a photon in the average pulse now. But when the detector does click, we can conclude there really was, on average, 1 photon in that pulse. And sure enough, you see this very nice, clear difference. All right, so that's the first measurement of the true single photon cross phase shift. Anyone who wants to talk about this later, I'd happily discuss it, but that's sort of the justification of this additional photon argument. But what I really wanted to ask about is when 1 photon can act like 100. In other words, are weak measurements good for anything? So you just ask roughly how much time do I have?
You still have about
Yeah, that ought to be perfect. So even though this is a little bit preaching to the choir, what was the line that Bill Phillips always used to like to repeat, which is that you should never underestimate the pleasure that people get from being told something they already know. So I hope that I can succeed in doing that. I'll reintroduce a little bit about weak measurement. Once more, we're going to have a pointer interact with a system, which is a generic way of describing basically every measurement we do. The pointer has some uncertainty in its position because everything does. And it interacts with the system through a Hamiltonian that looks like this. Hamiltonian originally due to von Neumann, where G is just some coupling constant. A is the thing we want to measure, whatever that is. And P sub x is the momentum of the pointer. And as Yakir pointed out earlier, that means it's the translation operator for the pointer. Operating on everything with this px would move the pointer a little bit. But how much does it move it by? Well, that depends on G, the coupling constant, and it depends on A, the thing you're trying to measure. If the measurement is weak, which either means that G is very small or just that this uncertainty is very big, then after the interaction, this wave function doesn't get shifted by a whole lot. Which means that on any individual trial, if I look at a pointer, it shows up somewhere within this distribution, and I can't tell whether it shifted at all, because it could have been anywhere in here when it began. But if we repeat the measurement many times, build up statistics, we figure out where that peak was, and we're able to extract information either about the coupling constant, if we know everything we need to about A, or about A, if we already know the coupling constant. All right, so those are two different kinds of applications of weak measurement. And as Yakir also pointed out, the nice thing is that if this is weak enough, it gives you essentially no disturbance to the system itself. Whereas a strong measurement takes a system and a probe and entangles them so that for each value of the system variable, you get a differently shifted probe wave function. And that entanglement, when you trace over the probe, is what leads to the effective uncontrollable disturbance to the system. When you do the weak measurement, to very good approximation, depending on just how weak you make it, you're left in a pure product state, no entanglement between the two systems, vanishingly small entanglement, where the system is undisturbed to first order, and the probe has simply shifted by this coupling constant times the expectation value of the thing you're trying to measure. That's with no post-selection at all. Well, now what if you add post-selection? We begin with this system in some funny wave function. We couple it to a pointer that could be pointing who knows where. And after they interact, we say, wait, I don't want to know about the value of A for all of the systems. I just want to know about those systems that started in the state I'm interested in and ended up in the next state I'm interested in, following that sort of trajectory. So let's do a projective measurement on the system and see whether it's in this good green state that we're curious about. If it is, then we're going to keep these data. And otherwise, we're going to discard them. We're going to say, no, that wasn't part of the sub-ensemble I'm interested in. So each time we get a keep, we'll look at the pointer and see where is the pointer pointing. So if you repeat this many times, well, sometimes you succeed. You take the pointer and you keep a record of it. Other times the post-selection doesn't give you the result you're interested in. You say, that's just not relevant for my current experiment. Throw it out. But you keep all these pointers and you build up a new distribution. And you ask, where are the pointers now? What's that average value? And this is what the AAV paper worked out. Used the standard rules of quantum mechanics to figure it out, and you find this weak value that you saw earlier. That tells you what the average effect on the pointer is. And we can then interpret that, or most of us here at least believe you can interpret that as describing what is the best description we have of this variable A for the subset of systems that started in state I and ended up in state F. Okay? And this is the formula that has all these fascinating mathematical properties, some that we like and shouldn't be surprised by, such as the fact that it reduces to an expectation value if you don't do any post-selection, or equivalently if you sum over all the possible post-selections, that it has linearity, that it behaves nicely according to all sorts of chain rules, etc. But it also has the funny properties you heard about earlier. It can be complex, unlike other expectation values. And if this inner product f dot I becomes really small, this can become arbitrarily large. All right? So you can get results on average that are way outside the eigenvalue spectrum for A, the thing that you thought you were measuring. And that's related to the super oscillations that you were hearing about before. So there's the question, is that good for anything practical? The answer of yes was already hinted at in the original AAV paper, but the first time it was used experimentally was in Hostin and Kwiat's paper, measuring something that hadn't previously been measured because it was so small. It's also because people weren't talking about it much, but the spin Hall effect for light, where they didn't do a very careful analysis of exactly what the gains do to using the weak value amplification were. They just showed we used this technique and we measured something really small, which was great. The more quantitative work began in John's group and with Andrew on this paper, where I can just never resist pointing out the results that they got measuring these beam deflections. And in this case, the beam deflection that they measured was 400 femtoradians, plus or minus 200 femtoradians. And I apologize to John and the others who've already heard me say this, but whenever I hear that number, I have to stop and try to figure out what it means. And the first time I went through it, I reached the conclusion that I didn't even believe when I got there, that what it meant was that if I took this laser pointer and managed to point it at the moon, but since my hand is kind of wobbly, and I've known to wobble by at least 200 femtoradians from time to time, that happened. My hand moved by 200 femtoradians. The center of the spot on the moon would shift by the thickness of a human hair. That's the sensitivity that these guys achieved, thanks to using weak value amplification. As most of you know, this goes back to the question of how the result of a measurement of a component of the spin of a spin 1/2 particle can turn out to be 100. And when thinking again about other variants on that problem at a previous Chapman workshop, I started to ask myself, well, can one photon act like 100 photons? And in fact, it grows directly out of another one of the famous paradoxes we periodically hear about here. But I wanted to use that in our light-matter interaction scheme, our nonlinearity scheme. So we've got the atoms here, some way that the red beam and the blue beam can be made to interact. The blue beam here is a probe. I've just built a little interferometer to measure its phase shift. And all that's really doing is measuring how many red photons are in here. And I said to myself, well, can't we use the same mathematics as for the spin? Can't we set up a situation where the weak value of the number of red photons is much greater than 1, even when you send in 1 photon at a time? Why do I talk about weak values? Well, remember, these are very weak interactions. We're seeing a phase shift of 10 or 20 microradians. We can't even measure that on a single shot because it's 1,000 times smaller than the quantum-limited phase noise of our probe beam. So we need to make 1,000,000 measurements to even see it. We're automatically in the weak regime. And wouldn't it be nice to amplify that effect up, make it easier to see? Have 1,000 microradians instead of 10 microradians. Well, we all know that any two-state system is equivalent to a spin. And if I take a photon and split it into 2 arms of an interferometer, that's mathematically the same thing as a spin that could be up or down. And if I say there's a way of getting the weak value of S sub z to be 100, that's equivalent to saying there's a way of getting the expectation value or the weak value of the photon number in one of these arms to be on the order of 100. In particular, the way it works out is if you prepare an initial state that's just A minus B over root 2, so a 50-50 superposition of the 2 paths in this interferometer, but with a pi phase shift. And you make a very unlikely post-selection. You post-select onto this detector firing, which has an amplitude related to RA plus TB. Well, if R and T were both 1 over root 2, this would never happen. So that would be a completely orthogonal state. But if R and T are 0.5 plus delta and 0.5 minus delta, then suddenly it just becomes a nearly orthogonal state. And the weak value of the number of photons in B turns out to be 1 over 2 delta. Make delta as small as you like, and the weak value gets really, really big, which means that the phase shift on the probe should be, in principle, 100 times bigger than the single photon phase shift, even if I just sent 1 photon in here and detected that 1 photon over here. That's what we mean when we say that the weak value of the photon number is 100. Its effect on some other system could be 100 times bigger than what it should have been. And I'll just tell you that we've seen this. We're still taking data, but these are the next to last data from my lab. The last data from my lab came in an email around midnight, and they were actually just extending this curve to confirm the single photon shift. But this dashed line shows you what I already told you, that we see something like 14 microradians per photon. And these points are what happen when we do appropriate post-selections. We've seen amplifications up to a factor of 4 or 5 over here. So we've really seen the weak value amplification of the photon number in a path. And this is the example I alluded to earlier of a real weak measurement where the system and the probe are distinct systems interacting weakly and thereby becoming a very little bit entangled. One optical beam interacting with the other optical beam. Okay? So there is the question of whether that's good for anything, and many of you know that this has become even more controversial lately with a number of papers such as this one. Weak value amplification is suboptimal according to Ferry and Coombs. And in fact, even a single coin toss classically can turn out to be 100 heads. The phenomenon of anomalous weak values, according to them, is not limited to quantum theory. Although, on the other hand, another paper by Matt Pusey then points out that anomalous weak values are non-classical in a very precise sense. And Lev Weidman, as always, has the pithiest response, which is that everything here just follows from Ferry and Combs' misunderstanding of the concept of weak value. The controversy has not ended. It suffices, as I told Yutaka a while ago, to wake up and check your Facebook page and see the latest papers. And if you wait a few minutes, you see the latest papers and about 300 people arguing about them. A while ago, it got to the point where when Facebook bored me and I decided to check the archive instead, the first 4 papers that I saw, 3 of them were about these arguments about weak values. And the other one was about the argument about D-wave. It's like you just can't escape this stuff. So I'm going to tell you a few words about part of our perspective on it. Our perspective is described in this paper and has since been more or less contradicted by basically everyone. Even the people like Andrew who seem to agree with me then go publish papers explaining why I was actually wrong all along. I'm waiting to hear more about that later. What I want to say is maybe a little overly political, but I'm really sincere when I say it, which is that I don't believe that the book is closed on this argument. I think each of us has our own particular perspective that we're approaching with, the kinds of measurements we're used to thinking about, the kinds of noise models we're used to thinking about, the kinds of resources we think are cheap, the kinds of resources we think are expensive, and I think really coming to a complete description of under which circumstances it's a good idea to do weak value amplification and under which circumstances it's not is going to remain a little bit of a complicated thing. Some of it is just language issues. It took me reading a bunch of these papers and confirming with people like Andrew what they thought the authors meant, and then recently actually having a chance to talk to Josh Coombs and confirm this misunderstanding. They seem to focus on the idea that post-selection means discarding things and make a big deal of the fact that you never gain information by throwing information away. I don't think any of us has ever contradicted that fact. That's kind of obvious. The question to us is whether you can get a huge amount of information in a small subsample, so huge that you might really not care about keeping the other 99% of the sample because it would have incrementally more information. Right? But along the way, for experimentalists, the question is really, should you do the measurement that we're calling a post-selection? And what I eventually realized is the theorists keep assuming that we've already done all these measurements, and we're just trying to figure out whether or not to throw away data. And what they didn't understand is we had to decide whether or not to buy the detector it would take to do the measurement. The question is, do you do that measurement at all? And if you do, what basis do you do it in? It's all nice to talk about the information in some joint state, but you still have to figure out which measurement do you do to optimize it. And in which regimes do those measurements end up looking like the weak value amplification case? So the background to all of this is that although you get the amplification, everyone has understood for a long time that in the most trivial setting, it won't help you to do it. Because what happens, if you throw away 99% of your data, then your signal gets amplified by a factor of 10. But those of you who have ever sat through a laboratory course should realize if you take 100 times more data, your noise goes down by a factor of 10. So you've got the choice of having 10 times more signal and also 10 times more noise, or 10 times less signal and 10 times less noise. So no advantage. And in fact, long ago when Jiva Anandan first alerted me to these possibilities and said, wouldn't you like to do an experiment on it? I did that back of the envelope calculation. And stupidly, I now say, said, no, there's no point. This is useless except in trivial cases. I wish I hadn't said that, but it's a good thing that others came back and figured it out. What we realized, though, is that although that means you'll never get beyond, let's say, the standard quantum limit just by doing the post-selection, once you have what we all tend to call technical noise, there are cases where you'll be able to reduce the technical noise. And people will talk later about exactly what they mean in different contexts by technical noise. I think it can mean very different things, and especially very different things when your signal is continuous, like an electromagnetic sort of classical field, and post-selection really means lowering its intensity, as opposed to cases where your signal is discrete, such as in our case, where we're looking at single photon pulses, and we end up with fewer pulses at the end of the day. These are very different situations, even though they fall under the same heading. So in our case, we were thinking about receiving some number of single photons per second, and the more single photons we get, the better our signal-to-noise ratio is. But if this line here is the shot noise limit, what we imagined is a case where there was some additional noise, as frequently happens, so that our signal-to-noise was lower than the shot noise. And all of these things get better and better as you get more photons, except it turns out that in the real world, there's some point where increasing the photon rate doesn't help you anymore. And this occurs because if you have more and more photons coming in on faster timescales than whatever fluctuations are giving you noise have a chance to change, you get no extra information about those fluctuating things. You can't keep averaging away the noise if the noise is staying constant. The way that you average things away is by waiting for them to change and measuring them again. And if within some fixed time you just keep measuring the same value of that noise field over and over again, it doesn't help you. So what we showed is that weak measurement lets you get around that, because by post-selecting, you essentially put the repetition rate of your signal slower and slower outside the correlation time of the noise, and yet you amplify the signal enough that you don't lose anything. So we saw that you could push this knee out further and further. And that's one example that I still believe we're probably going to find works. There have been some arguments about alternate ways of treating similar systems, but I suspect that this is still better even in principle, and even if I'm wrong about that, I'm very confident that there are going to be regimes where it's better in practice in terms of the resources required to do the alternate treatment. So I just want to contend that weak value amplification is at least sometimes useful. I don't think we have a complete description of in which cases it is and isn't. But clearly, if you're limited by detector saturation, you have to turn down the intensity of your source. I've done many experiments where we had to turn down our lasers so as not to burn out our detectors. Well, if you're going to turn the laser down anyway, do you want to do it the stupid way and leave the signal just as small as it always was? Or do it by doing post-selection and amplify the signal at the same time? Obviously, in that case, it makes sense to do post-selection, take use of weak value amplification. There are other cases that just have to do with simple classical statistics where it makes sense to do this kind of post-selection. In our experiment, if we send in pulses with 1/10 of a photon per pulse and try to measure the average phase shift, well, we could measure the average phase shift per pulse and then multiply it by 10 to get the average phase shift per photon. But we'd be including 9 noise pulses for every signal pulse we had. If instead we post-select on there being a photon and only use the 1/10 of the pulses that actually contain photons, we can measure the same signal with lower noise. All right, that's a clear statistical argument. And again, the one I was talking about was the noise correlation time, where we believe that even if you argue that there are other ways using principal value decomposition and so forth to treat these cases of correlated noise, the expense of getting enough information about the noise and doing that processing would probably be larger than the difficulty of just doing the weak value measure. All right, so that's all I wanted to tell you about that, but if I still have a little time, there's one other topic that I wanted to introduce. This is part 10 of my talk in binary, and this is on quantum data compression, which was inspired by a nice talk I heard by Robin Bloom-Cahoot, but work that we did in the end with Peter Turner. And it's motivated by the following question. How much can we compress an ensemble of identical qubits? Thanks. You know that we all compress classical data all the time. We make our JPEG files and whatnot. But what about quantum data? Well, compressing an ensemble of identical qubits might seem a little strange because they're all identical. How many copies do you need? With classical information, I could learn everything I wanted from one copy of a bit. right? If you take a book and you fill it with the letter C, you don't really need to carry the whole book around. I can just tell you it's filled with the letter C. That's all you need to know. The same is not true quantum mechanically. Oh, I forgot about that. Truly marvelous proof that information is infinitely compressible, which means 5 minutes will do just fine. What about quantum data? If I give you 8 copies of identically prepared photons, but I don't tell you how they were prepared, you can't just keep the first copy and say, oh, it's okay, I've got all the information. Because if you look at that photon, any measurement you make will give you one classical bit of information, while it takes an infinite amount of information to actually describe the state perfectly, if you ever could. Every photon I give you in the same state gives you a little more information about which way it was actually pointing. So the question is, do you need all of them? Or is there some way you can compress that? There's clearly some redundancy here after all. Okay, I already said all that. All right. So here's the game. We have Alain sending Bob n qubits. They're all prepared in the same state. And I talk about trying to figure out what state the bits are in, but honestly, we never do that. That's meaningless. We're always getting approximate information that we use to write down mathematical objects that we use to predict the results of future measurements. So what's the game, really? I'm telling you, if I give you some more of these photons later on and you make a measurement, how do you think it's going to turn out? That's what you're asking me to do, predicting the outcome of future measurements. And the wave function or the density matrix or whatever else, those are tools towards that end. So suppose that Alain is later going to ask Bob to predict some spin projection. What should Bob do? Well, it depends. If Bob can just hold on to the photons, then that's what he should do. He should wait until Alain says, I want to know sigma x. And then Bob says, fine, I'm going to measure sigma x on every one of the photons. And I now have lots of information. Of course, typically we don't do this because we don't have big quantum memories. Most of us don't have quantum memories at all. In fact, I'm losing my classical memory as time goes on. If you have no memory, you instead do something that we call quantum tomography, which, again, Yukio was describing earlier, essentially means you take 1/3 of the particles, you measure x, 1/3 you measure y, 1/3 you measure z, and you say, all right, now I've kind of got information about everything. You write down a density matrix, and it's a nice trade-off. No matter what Alain asks later on, you've got information about it. But when he asks about z, what answer are you going to give him? Basically, it'll come down to looking at the 1/3 of the particles you measured along z. The ones you measured along x, the ones you measured along y, they were wasted. They gave you no information. So if you had some memory, this was our hope, maybe instead of storing all the qubits, you could store a smaller number, but still be able to do the right measurement later on to figure out the best answer to Alain's question, or at least come close. In fact, at first I thought this would be a lossy compression. Turns out it's not. It's lossless. Now let's do the hand-waving argument. How much memory should it take? And we can begin classically, and we'll get the right answer. So suppose you wanted to know the expectation value of S sub z. What would you do? You'd measure S sub z n times. So you get a list of numbers, n zeros or ones, and you just take n up minus n down over n, divide that by 2. That's the answer. How would you store that information? Well, I could write out my data stream, a list of n zeros or ones, but I don't care about the order of those zeros and ones. I don't care about the permutation, right? That's because these particles were identical anyway. What I care about is how many were up, how many were down. So I need to write down one single number, n up, which is somewhere between 0 and n. How many bits does it take to write down a number between 0 and n? Not n bits, but log n bits, or log of n plus 1. So that's the answer classically. You just write down that number. And it turns out that's the answer quantum mechanically as well. If you can write down that number, but also be able to write down coherent superpositions of all possible values of that number, you actually have all the information you need in any basis. And that's related to the fact that although I've got a 2 to the n dimensional Hilbert space for my n qubits, if they're all prepared identically, and so far we're dealing with pure states, we haven't yet extended beyond that, although that's the next step, they live in the symmetric subspace whose dimension is only n plus 1. So since that's a smaller dimensional subspace, we can compress it. 7 qubits could be compressed into 3. 999 could be compressed into 10. We're experimentalists. We had to live with compressing 3 into 2 because that's an exponential advantage. So we go from 3 to log of 3 plus 1, which is 2. And I won't go into the details of how it works. It's based on a mathematical transform known as the Schur-Weil transform, whose implementations were described in these two papers by Bacon, Schwang, and Harrow, and Plesch and Buzek. And thanks to Pete Turner and to my student Lee Rosema, we figured out that you can take this rather insane-looking circuit. Well, I mean, it's not insane as a circuit, but for those of us who try to build quantum circuits for light, that was just, laughable. I fell on the floor when Peter found that one in the Bacon, Schwang, and Harrow paper. But what's the idea here? You have three identical qubits coming in, and they go through this funny operation. And what you end up with is an entangled state of these two qubits and just a 0 over here on the end. You can throw that third qubit out. It contains no information because you already knew you were in the symmetric subspace. So basically what you end up with is a superposition of 4 different values for this register. The value that said there are 0 spin-ups, 1 spin-up, 2 spin-ups, or 3 spin-ups in binary with the correct binomial expanded amplitudes over here. So what did Lee manage to do? He realized that since we don't care about the third qubit anyway, we can just post-selectively disentangle it. We can get rid of those 2 gates I didn't know how to do. He then realized that if we take 2 of the qubits and store them in different degrees of freedom of 1 photon, and the third qubit in a second photon, then suddenly all the gates between these first 2 qubits become trivial. They're within 1 photon. And all we have to do is these 2 gates conditioned on the second photon. But then again, these 2 gates are both conditioned in the same way, so that's just one conditional unitary. And if we just take that controlled unitary and use some tricks known as shortcuts through higher dimensions, you can turn that complicated circuit into this relatively simple optical experiment. So I know this might look more complicated than the original circuit, but if we hadn't had these shortcuts, it would have looked more complicated. This one at least was actually feasible. And here are the results. We encoded a bunch of different states in 3 qubits, threw out 1 qubit, and then did the appropriate measurements to extract X, Y, and Z on each of them, and looked at the variance, looked at what uncertainties we got when we only had 2 qubits to measure, and compared them with a simulation for doing a measurement on 2 bits or doing a measurement on 3 bits. Now what you find is we had just as much information in our 2 entangled bits as you would have had if you'd begun with 3. So that's perfect timing. In summary, I'll just say, again, we used electromagnetically induced transparency in cold atoms to observe this nonlinear cross-phase shift due to individual photons. We went on to do the right post-selection and see that we could make it much larger than the single photon phase shift, and are still moving towards experimental studies of the signal to noise and exactly how well that can improve our signal. And finally, all the information that you could extract from an n-qubit ensemble of identically prepared pure states about any observable can be compressed into log of n plus 1 qubits for later extraction. I find that really interesting for fundamental reasons. We're exploring with some friends whether it might actually have applications to quantum computation as well. Thank you very much for your attention. Hi.
So I'm sure you actually know this, but I just thought I would. I'm usually loud enough, but I'll use it. I just thought I would comment on the way we interpret compression normally is a little different than what you're describing. We're not trying to compress a book full of the letter C, but we assume the ensemble for each letter in the book is the same. That is, if you chose a letter at random, it would be equally likely to be, drawn out of the probability distribution. And the same is true for quantum compression. So we don't assume that the pure states are all the same, but that there's some underlying pure state of your n systems where the ensemble is such that it looks like n. A tensor product of n copies of the same density matrix. So what you're doing seems to be actually something rather different from that.
Almost complementary.
You're looking at the case. It's more like an exchangeable state where the states are all the same. You have a source that produces n copies of exactly the same state, but you don't know what the state is.
Exactly. So yeah, I should have said that this is very different from standard like Schumacher compression. Yeah. And in particular, when we compress classical data, the idea is given knowledge of the symbol frequencies, we can store the message, which means basically the ordering of those symbols more compactly. And here we're trying to do exactly the reverse. and say, we don't care about the permutation order because we began with identical systems for purposes like tomography. And what we're trying to do is just compress information about the symbol frequency table, about the state itself. And yeah, I should have said at the beginning, it's completely different from what many people mean by data compression. Thank you.
Yeah.
Okay, other questions?
So my question is about this non-linearity of the single photon. Is the last night's last night experiment data is surprising for me. Such kind of the cross-phase modulation was observed, but it's just now is you show that the fitting curve of this is not single level, a single photon level. You mentioned about it, but what's happening of that between the gap is the experimental data and the single photon non-linearity.
I'm not sure I understood the question, but perhaps I did. You're right that although we're doing the experiment at a single photon level,
right.
We're not currently doing it with true prepared single photons.
Yeah. No. It's next one, I
The
think.
next one? Oh, I see. This over here?
Yeah.
Okay. So this is essentially just a classical statistical analysis, Bayesian analysis, saying that if I send in a pulse that has some average incident photon number, but of course Poisson statistics around that, and then I get extra information. After my inefficient collection and my inefficient detector, the detector either fires or it doesn't. First, let's make two assumptions. Let's assume that I had a photon number resolving detector. It could tell 0 from 1, from 2, from 3. It can't, but just pretend that. And pretend that I had no background at all. Then it turns out that if you infer the photon number, come up with the average of your conditional probability distribution for how many photons there were, given that there was no click, or 1 click, or 2 clicks, or 3 clicks, or 4 clicks, you find a series of parallel lines separated by exactly 1. And of course, their weighted average will just be the 45-degree line that says, well, the average photon number was equal to the average photon number. When you add in the fact that there is background, my detector might fire even if there are no photons, then you get some funny curvature down here when you have low photon number. And when you take into account the fact that if 2 photons hit my detector, I can't tell, it still just clicks. When I really see a click, I see something more like this blue curve that's now got contributions from the 1 click and the 2 click and the 3 click and the 4 click. So that's why they're not exactly parallel. But right, what we're looking at is we're trying to stay in a regime where it's close to this parallel 0 click and 1 click case and look at the difference between the two. And the argument is that there's essentially a mode that gets detected, and then there's everything else in the universe. And those things are not entangled. They're just split at some effective beam splitter. So when my detector fires, I get information about that mode. But because there was no entanglement, I learn nothing about the other modes. So if you ask me, revise your estimate of how many photons are in all the other modes, I say, I don't need to revise it. It hasn't changed. But what's your estimate of how many photons reach the detector? Well, now that's 1 instead of 0. So my estimate of how many photons were in the interaction region just went up by exactly 1. It's the photon that clicked. So by looking at the difference, we're really seeing the nonlinearity due to the photon that clicked, subtracting out all the other photons whose number we didn't even really know. And at the moment, the same is true for the weak value experiment. So, we advertise it as trying to make 1 photon act like 100. And actually, so far, what we've done is make let's say we've made 100 photons act like 105 photons. And we're trying to argue that it's that 100th photon that's acting like 5 photons, and the other 99 aren't doing anything interesting. But we need to move a little bit beyond that.
Okay, let's thank Aephraim again.
Thank you.